Good morning, everyone. I'm Shravani Kurma. I would like to present a journey across the globe, unveiling the tapestry of an international PhD student's life in Taiwan. The contents of this presentation are introduction, the activities involved in my school, and the lab environment, our day-to-day life, the faculty appreciating our work, my research activities in wireless communications. Coming to the first part, introduction. Embarking on academic adventure, my journey at NSYSU. As I already mentioned, I'm Shravani Kurma. I'm pursuing my PhD in wireless communications at NSYSU. If you can see, I'm an Indian in Taiwan. This is our campus. And the slide two, the activities involved by uh, the activities in our school. So beyond academics, we got involved in most of the holistic activities at NSYSU. As you could see, the softball, badminton, and the walking challenges which we have taken place, and the stretching your muscles, not just your mind, sports opportunities for PhD students. If you can see, there is a dragon boat competitions held in our school in Kaushan, and this is one of our races, and this is a team. If you can see, this is first match. We won second prize in dragon boat. Um, this is a school team of NSYSU. And not only sports, we got involved in international cultural events as NSYSU. As I'm very fond of dancing, these are a few performances of mine at different incidents in at NSYSU. One is during Diwali event, other one is like the international cultural events at NSYSU. And this is a lab environment. Like inside our innovation hub, the lab life at NSYSU will be like this. So we do have parties and we do have environments where we have serious researchers, and every lab has mostly like master students, PhD scholars, and postdoctorates along with the professors. If you can see the day-to-day life, the rhythm of the research is like day life as a PhD students will be like we just follow the ideas, not the clock. The freedom of the PhD life is like we can work anytime we want, provided we need to work for 16 to 18 hours a day. As you could see, we do have a faculty who are so supportive that more than just a tap on our back, our NSSU professors value our work and us with a token of appreciation from them for each and every activity we get involved with. So my research in wireless communication deals like, if you can see, the word wireless communication means the communication happens through a wireless media. So that means from the base station, if you want to communicate using your mobile, there is no connection, there is no wire. So wireless communication, the communication with wireless media. If you can see, the applications are like, there are so many applications for the wireless communications, including our mobile phone. If you can see, there is no connection from the base station to our mobile phone, but still we can communicate. Similarly, there are smart TVs, satellite communications, Wi-Fi, Bluetooth. These are all the applications of the wireless communications. And there are two research areas in wireless communication. One is like performance analysis, other one is like optimization. So let us understand these two terms in detail. If you can see, uh, let me take an example. This is a cat, and you can see there is a router. So if you got a new router and if you want to check how well it is performed, so what do? You check the internet speed. That means you are checking the speed of the internet to analyze the performance of a device. So this is how the performance analysis is done. That means we are going to analyze the performance of the system. And the second one is like optimization. Let me take an example of the same router, but we are not receiving any signal. That means we found like no network. So what do? We change the router position from one place to another place so that we get proper signal. That means we are optimizing the location to get proper signal. This is called optimization. And if you can see, this is my project, like RAS digital twin system metaverse. So the physical network, as you could see, the physical network is replicated into virtual. That means we could able to replicate the same physical network into virtual network, and we are going to analyze the virtual network. Because if we want to analyze the physical network, it includes so many parameters and it involves cost. But if you want to apply any model, it involves complexity, time taking, everything. But if you can create the replica of the physical thing to a virtual mode, we can analyze its performance or optimization whatsoever using different models on the virtual network without any implementation of the complexity or the cost. And during this, if you can see the system model of it, this has a base station and there are users and the RAS. So when there is no direct communication from the users to the base station, we use an RIS, reconfigurable intelligent surface, which can reflect the signals from the users to the base station or vice versa. This system is uplink, that means only from the users to base station, the signals will be transferred. So under this case, the RIS is providing a connection from the users to the base station, and we need to analyze the performance of the RAS now. So how do we do that? If you can see, the RAS has small parts in it, like the passive elements on it. So these reflecting elements are given on the x-axis, and the time taken for the whole system to operate one particular task is given on the y-axis. So if you have no RAS, or if without RAS, even if you increase the number of elements, there is no RAS, so there is no impact, so it is a straight line. And if you can see the RAS, and the time is also involved will be more. And if you can see, there is an RAS, but it is sending signals randomly to different places, but not to the specified place we are intent to send. So that means random phase shifts. When we use random phase shift, it represents that there is a latency. There is latency which is higher than the optimal phase. So if you can see this black one is like without RAS, this red one is like optimum RAS. That means it is exactly sending to the place where we want to send. And this is randomly. Randomly means sometimes it may, by luck, it may touch the desired place also, but it is not intended to send to the desired location. And coming to the other project, that is RAS aided full duplex MIMO, in which you can see a base station and there are some uplink users and some downlink users and two RAS. So with the aid of RURAS, the base station is getting served by the base station is receiving signals from the uplink users, and all the downlink users are getting served from the base station using RDRAS. So in this case, we can able to see that the uplink users may send some signals to the downlink users. That means that there might be some interference happens. That means co-channel interference. And as you could see, the base stations involve some self-interference, where as it continuously, like at a time, full duplex means at a time it is sending and receiving. So due to sending and receiving, there might be self-interference at the base station. So we are going to analyze these two interference in detail. If you can see there, if there is more interference, the efficiency will be very less. The efficiency decreases as there is more self-interference. At the same time, the y-axis, this green and the red line indicates that the RAS interference. As there is more RAS, means more self-interference, this is more in self-interference, then the rest of the efficiency decreases. So whatsoever the interference, the efficiency decreases with interference is the concept. And if you can see the blue line, it represents half duplex. That means there is no effect on the half duplex. Means in half duplex, only sending or receiving happens, but not both at a time. That means it doesn't have any interference from the co-channel or even self-interference. That's the reason why it doesn't have any change. Thank you for listening to me. And it would be great if I can answer to any of your questions if you have. Thank you.